Hello, we are Group 1 of the Spring 2018 Senior Lab. Our group members are Logan Gordon, Alex Mesnil, and Joseph Mitchell. In this video, we will be completing the caffeine extraction experiment. The primary purpose of this lab is to observe the different conditions that affect caffeine extraction and determine which variables have the greatest effect. The variables available to us to experiment with are the size of coffee grinds, temperature, flow rates, mass of coffee, and separatory funnel inversions. We decide to vary the size of the coffee grinds between coarse, medium, and fine, the flow rates between approximately 1.84, 2.5, and 3.35 milliliters per second, and the inversions between 4, 8, and 12. The theory behind this experiment has to do with extraction, which is a technique used to isolate one compound from a liquid solution. Dichloromethane is used to separate caffeine from water because caffeine is more soluble in dichloromethane. Solubility is driven by the balance of intermolecular forces between the solvent and solute. Caffeine travels from the aqueous phase to the dichloromethane phase through diffusion. The two liquid phases separate because of the differences in their densities. Water has a density of 1 gram per centimeter cubed, and dichloromethane has a density of 1.33 grams per centimeter cubed. Therefore, it will sink to the bottom and the aqueous phase will remain on top. Finally, the concentration of caffeine in the dichloromethane solvent is determined by using a calibration curve. The theory behind the calibration curve is Beer's law. In the Beer's law equation, A is the absorbance, E is the molar extinction coefficient, L is the path length, and C is the concentration. Safety glasses, lab coats, and nitrile gloves should be worn throughout this entire experiment. Only handle dichloromethane when wearing silver shield gloves, and only open dichloromethane under the hood. Aqueous and organic waste should be disposed of in the appropriate waste containers.
Start off the experiment by heating your water to its desired value. Calibrate the flow meter for whatever flow rates that you choose to manipulate within the experiment. Now it's time to grind up some beans. Select your coarseness setting and be sure to take a whiff of some of the finest coffee E2 has to offer. Place the coffee beans into the bag at your desired weight. After you reach your desired weight, it's time to staple that bad boy up. After determining your reactor volume, place the coffee bag in the reactor and get ready to extract some coffee. Extract 3 different samples at 3 different time intervals of your choosing. Transfer your 15 milliliter sample of coffee, while also transferring 15 milliliters of dichloromethane. Be sure to wear silver shield gloves as dichloromethane is quite hazardous. Once we've brought DCM to the party, it's time to invert the separatory funnel. You will see that the two separate into 2 distinct phases, making it easy for separation. Separate the organics mixture into a separate beaker. We then transfer the clear dichloromethane phase liquid into a quartz cuvette and place into a spectrophotometer. After it's placed in nice and gently, we record the absorbance at 275 nanometers.
All right, nice. Thank you, Alex and Joey, for that fantastic description. Moving on to the data analysis involved in this lab. Here we can see the calibration curve needed to convert that absorbance we just found into a concentration of caffeine. Known concentrations of caffeine were measured in the spectrophotometer, and resultant absorbances were found, and this graph is generated. Using the equation from the line of best fit, we can plug our found absorbances into the in for y and find the x, the concentration of caffeine. Before we dive into our data, the calibration of the flow meter mentioned earlier can be seen here. Since there are no units on the flow meter, we need to calibrate the numbers on it to actual flow rates. We did this by setting the 3 flow rates we were testing and collecting water flowing out of the meter. We timed how long it took to collect various amounts of water, and then weighed that water and converted it to a volume using the density of water at 60 degrees Celsius, our constant temperature throughout this experiment. The volume was then divided by the time to collect the water, and the 3 flow rates we found can be seen here on the right column. For those three flow rates, we can see the resulting concentrations of caffeine collected at 3 points in time. It can be seen that flow rate has a dramatic effect on the concentration. The lower the flow rate, the higher the concentration of caffeine collected, which makes intuitive sense as that lower flow rate corresponds to a larger residence time. It should also be noted that as time progresses, the concentration also generally increases. In this figure, we show the effect of the number of separatory funnel inversions on concentration over time. Again, there is a general increase in concentration as time progresses. Now, with the 4, 8, and 12 inversions, we don't really see a trend here for the effect of amount of caffeine collected. It was predicted more inversions would result in a higher concentration, as the DCM would be allowed to contact the caffeine much more, but that was not seen. In this final graph, we can see the effect of grind size on the concentration. Again, a general increase in concentration with time is seen. It was inferred a smaller grind size would result in a higher concentration as there is more surface area to react. However, this was not the case, as it generally seems the opposite is true, as the coarse and medium sizes generally produced a higher concentration. However, these sizes are inexact, as we are just relying on the coffee grinder to give consistent sizes, so there is definitely some room to further interpret this set of data. In conclusion, of the 3 tested variables, flow rate produced the most notable and expected trend, with that inverse relationship we observed. The number of reversions showed no trend, and the change in grind size showed larger grounds produce more caffeine, which was slightly unexpected. And while time was not specifically tested, a general trend of concentration increasing with time was observed. There were also some parabolic moves, or peaks, on the graph, leading us to believe there is an exact time where the most caffeine can be collected. With all that being said, we hope you got something useful out of this video, and we appreciate you taking the time to watch it. Thank you.